Namaskar and I welcome all of you to my YouTube channel. This is lecture number 4 on magnetic properties of solids. Today I am going to teach you LANGEVIN'S classical theory of diamagnetism. Students, in this lecture my main target is to derive a mathematical expression for magnetic susceptibility of a diamagnetic material. Since it's a very lengthy topic, so first let me talk about the intermediate steps that I am going to follow while deriving the expression. In step number 1, we will consider a 1 electron atom in absence of any external magnetic field and we will calculate the angular frequency of this electron. Okay? So, in step number 1, we will calculate angular frequency of the electron when external magnetic field is 0. In step number 2, we will apply some external magnetic field on this 1 electron atom system. Because of the application of external magnetic field, the angular frequency of this electron will be changed. So, in step number 2, we will calculate the new angular frequency of this electron in presence of external magnetic field. Okay? Step number 2. Calculate new angular frequency of the electron when magnetic field is present. Again, due to the change in angular frequency of this electron, an induced current or an induced magnetic dipole moment will be developed. So, in step number 3, we will first calculate the induced current and then induced magnetic dipole moment. Okay? Step number 3. First, calculate the induced current due to change in angular frequency of the electron and then induced magnetic dipole moment. So, this is the magnetic dipole moment for 1 electron and 1 orbit atom. Okay? Next, we will extend this concept to an atom having large number of electrons and large number of atomic orbits. Okay? So, in step number 4, we will calculate the magnetic dipole moment of many electron and many atomic orbits atoms. Okay? Next, in step number 5, we will calculate the magnetization of a diamagnetic material having n number of atoms per unit volume. Okay? Calculate magnetization of a diamagnetic material having n number of atoms per unit volume. Okay? Finally, in step number 6, we will calculate the susceptibility of a diamagnetic material by using this relation: magnetization per unit magnetizing field. Okay? So, these are the 6 steps that I will follow while deriving the mathematical expression for magnetic susceptibility of a diamagnetic material. Now, let me explain the theory part. First, we are considering a simplest 1 electron atom in absence of any external magnetic field. We assume that this electron is revolving around the nucleus in anti-clockwise direction with angular frequency omega naught. The mass of the electron is m and charge of this electron is minus e. Okay? First, let me write these points. Let us consider a simplest type of atom in which an electron of mass m and charge minus e is revolving around the nucleus in anti-clockwise direction with angular frequency omega naught in absence of any external magnetic field. Students, to sustain circular motion, the magnitude of electrostatic force between electron and nucleus must be equal to the centrifugal force of this electron. Okay? To sustain circular motion, the electrostatic force must be equal to the centrifugal force, that is, magnitude of electrostatic force is equal to magnitude of centrifugal force. Okay? Students, here we assume that the radius of this atomic orbit is rho. Okay? So here rho represents the radius of this atomic orbit. Again, the magnitude of electrostatic force between electron and nucleus is given by 1 by 4 pi epsilon naught q1 q2 divided by rho square. So here q1 is the nuclear charge, whose value is Z into E. Q2 is the electronic charge, whose value is minus E. Since we are considering only magnitude, so magnitude of electronic charge will be E. Okay? So finally we will get the magnitude of electrostatic force as 1 by 4 pi epsilon naught ZE into E, Z E square divided by rho square. Next, the magnitude of centrifugal force is given by m v square divided by rho. We know that v is equal to rho into omega naught. So ultimately the magnitude of centrifugal force will be m omega naught square into rho. Okay? M omega naught square into rho. So after simplifying, we will get omega naught as root over Z E square divided by 4 pi epsilon naught m into rho cube. ठीक है. So this is the value of angular frequency of this electron in absence of any external magnetic field. Next we apply some external magnetic field on this one electron atom system. We assume that the strength of magnetic field is B and it is directed along positive Z direction. That means it is coming out of this board. Because of the application of external magnetic field, this electron will experience a magnetic force along negative x direction or towards the center or towards the nucleus of this atom. Okay? Now let me write these points. If an external magnetic field is applied then magnetic force acting on the electron will be Q into V cross B. We know that electronic charge is minus E. Velocity vector magnitude is V and it is along the y direction. So this can be written as V into y cap cross B vector. B vector is B into z cap. After simplifying, we will get minus E V B into y cap cross z cap whose value is x cap. ठीक है. Again, the velocity of this electron can be written as rho into omega, where omega is the new angular frequency of this electron after application of external magnetic field. So finally we will get after rearranging we will get E rho omega into B minus x cap. So here we have seen that after application of external magnetic field along positive z direction, this electron will experience a magnetic force along negative x direction. ठीक है. So this is the direction of magnetic force on this electron. Now the force equation can be written as electrostatic force plus magnetostatic force is equal to centrifugal force plus magnetostatic force is equal to centrifugal force. In my previous section, I already calculated the value of electrostatic force, whose value is 1 by 4 pi epsilon naught into Z E square divided by rho square, and the value of magnetostatic force is E into rho omega into B, and the value of centrifugal force is given by m omega square into rho. Here we have written the value of centrifugal force as m omega square into rho, because after application of external magnetic field the angular frequency of the electron is changed from omega naught to omega. ठीक है. The value of this term according to previous section is given by m omega naught square into rho minus e rho into omega b is equal to m omega square into rho. After rearranging, we will get omega square plus eb by m into omega minus omega naught square. This is a quadratic equation. The value of omega can be obtained by using this relation minus b, that means eb by m plus minus root over b square eb by m whole square minus 4ab. 4ab means plus 4 omega naught square divided by twice a divided by 2. So after simplifying, we will get omega as, so first let us divide this term by 2. So we will get plus minus root over omega naught square plus eb divided by twice m whole square. Next, let us divide this term by 2. So we will get minus eb divided by twice m. Now let us take one special case. For eb divided by twice m very less than omega naught, this equation 2 becomes omega almost equal to plus minus omega naught, because in this case we can neglect this term, minus eb divided by twice m. So we have seen that after application of external magnetic field, the angular frequency of this electron is changed by the factor eb divided by twice m. ठीक है. Now let me write this point. This shows that in presence of external magnetic field, the angular frequency of orbiting electron changes by a factor eb by twice m. Students, due to change in angular frequency of this electron, an additional current will be developed and we are going to calculate this value. ठीक है. The change in angular frequency produces an additional current which is given by I induced is equal to, we know that current is defined as Q divided by T. ठीक है. Charge into revolutions per unit time. In our case, the charge of the electron is minus E, and revolutions per unit time can be calculated by using this relation. Students, we have found that the change in angular frequency of the electron due to the presence of external magnetic field is given by E B divided by twice m. this term can be written as twice pi by t. So therefore, the value of 1 by t is given by 1 by twice pi into EB divided by twice m. ठीक है? So 1 by t value will be 1 by twice pi into EB divided by twice m. After simplifying, we will get the value of induced current as minus E square B divided by 4 pi m. Again, magnetic dipole moment produced due to this induced current is given by the magnetic dipole moment produced due to induced current is given by I induced into area of this loop. The value of induced current is minus E square B divided by 4 pi m, and area of this loop is pi rho square. So after simplifying, we will get mu E as minus E square B divided by 4m into rho square. Here negative sign indicates that the direction of magnetic dipole moment is opposite to the direction of applied field. ठीक है? Here negative sign indicates that direction of magnetic dipole moment is opposite to the applied field. ठीक है? Please note down that this is the expression for magnetic dipole moment for one electron and one orbit atom. ठीक है? Next we will extend this concept for large number of electrons and large number of orbits atom. ठीक है? So if the atom has z number of electrons and all the atomic orbits are randomly oriented like this, then net induced magnetic dipole moment will become z into minus E square B divided by 4m into average value of this quantity. Now let me write this point. If the atom has z number of electrons and all the atomic orbits are randomly oriented, then total induced magnetic dipole moment becomes mu A is equal to minus z into E square B divided by 4m into average value of radius square. Here we assume that the radius of first orbit is rho 1, radius of second orbit is rho 2, radius of third orbit is rho 3, and so on, and the average value of radius square is given by this quantity. ठीक है. Again, since the magnetic field is applied along z direction, so therefore the motion of electrons will be confined in xy plane only. ठीक है. Suppose this is equation number 3. Since the magnetic field is applied along z direction, so the motion of electrons will be confined in xy plane only. Therefore, average value of rho square can be written as average value of x square plus average value of y square. Suppose this is equation number 4. Again, average radius of all the atomic orbits or mean square distance of the electrons from the nucleus is given by, again, average radius of all atomic orbits or mean square distance of the electrons from the nucleus is given by average value of r square is equal to average value of x square plus average value of y square plus average value of z square. Suppose this is equation number 5. For spherically symmetric charge distribution, for spherically symmetric charge distribution, average value of x square is equal to average value of y square is equal to average value of z square. If we substitute this value here, then we will get, therefore equation 5 implies average value of r square is equal to 3 into average value of x square. Suppose this is equation number 6. ठीक है. And equation 4 implies average value of rho square is equal to 2 into average value of x square. Now comparing equations 6 and 7, we get comparing equations 6 and 7, we get average value of rho square is equal to 2 by 3 into average value of r square. Suppose this is equation number 8. Now let us substitute the value of average value of rho square in equation number 3. ठीक है. Substituting the value of rho square in equation 3, we get mu A is equal to minus Z into E square B divided by 4m into average value of rho square, whose value is 2 by 3 into average value of r square. After simplification, we will get minus Z into E square B divided by 6m into average value of r square. Again, we know that B can be written as mu naught into h. So after substituting this value here, we will get mu A as minus mu naught into Z E square into h divided by 6m into average value of r square. Suppose this is equation number 9. Again, if a diamagnetic material contains n number of atoms per unit volume, then magnetization of that material will be given by n into mu A. Now let me write this point. If the diamagnetic material has n number of atoms per unit volume, then magnetization of that material will be m is equal to n into mu A. So final value will be minus n into mu naught into Z into E square into h divided by 6m into average value of r square. Suppose this is equation number 10. So magnetic susceptibility of diamagnetic material becomes m divided by h, whose value will be minus n into mu naught into Z E square divided by 6m into average value of r square. Now let me write this point. In this case, magnetic susceptibility becomes m divided by h, which is equal to minus n into mu naught into Z E square divided by 6m into average value of r square. So this is the Langevins classical theory of diamagnetism. ठीक है? Suppose this is equation number 11. This is Langevins classical theory of diamagnetism. Conclusions. Langevins classical theory tells that diamagnetic susceptibility is negative and independent of temperature. Number 1. Diamagnetic susceptibility is negative and independent of temperature. Number 2. Diamagnetic susceptibility is directly proportional to n. That means diamagnetic susceptibility depends on size of the atom. depends on size of atoms. ठीक है. Number 3, diamagnetic susceptibility is directly proportional to average value of R square. That means outer electrons make largest contribution to diamagnetic susceptibility. Outer electrons make largest contribution to diamagnetic susceptibility. ठीक है. Finally, let me explain you one very important point. Students, in my previous section, I already mentioned you that after application of external magnetic field, the new angular frequency of the electron becomes plus minus omega naught minus EB divided by twice m. Now, let us understand under what condition the new angular frequency becomes plus omega naught minus EB divided by twice m, and under what condition the new angular frequency of the electron becomes minus omega naught minus EB divided by twice m. Students, this positive sign indicates that orbital magnetic dipole moment is parallel to the applied field, and when the orbital magnetic dipole moment is parallel to the applied field, then new angular frequency of the electron is decreased by the factor EB divided by twice m. Again, this negative sign indicates that orbital magnetic dipole moment is antiparallel to the applied field, and when the orbital magnetic dipole moment is antiparallel to the applied field, then new angular frequency of the electron is increased by the factor EB divided by twice m, and this is known as the Larmor's theorem. I will explain this topic in detail when I teach you atomic physics topic. ठीक है. Finally, I have drawn a magnetization versus magnetizing field curve for a diamagnetic material. When magnetization is taken in positive x direction, then M versus H curve for diamagnetic material will be like this. When we take minus M along positive x direction, then M versus H curve for diamagnetic material becomes like this. ठीक है. This is all about today's video, and I hope that you have learned a lot from this video.